In this problem, we're asked to find the unique polynomial with real coefficients that meets these conditions. And the conditions are degree 4, having these zeros, and then f of 0 equals 30. Well, right off the bat, we know that because this polynomial has real coefficients, the complex conjugate pair theorem tells us that if x equals 2 minus I is a root, x equals 2 plus I is also a root. And a corollary of the factor theorem tells us that given a list of roots, we can write out a factorization, a linear factorization of the polynomial in the following way. We have a leading coefficient that is some value that we don't know. And then from x equals 3 being a root, we know that x minus 3 is a factor. Also, x plus 1 is a factor. Then x minus 2 minus I is a factor. And also x minus 2 plus I is a factor. And then we also know that f of 0 equals 30. Well, that allows us to solve for the a value here. So I'm going to write out solve for a value by plugging in the point 0, 30. So we're going to replace f of x with 30 because we're plugging in 0 for x. And then we're going to replace all of the x values with 0. Then we get 30 equals a multiplied by negative 3 multiplied by 1 multiplied by negative 2 minus I, negative 2 plus I. Then we get 30 is equal to a multiplied by negative 3. And these two factors multiply to give us, so each of these factors has a factor of negative 1 in it. So this is going to be the same as 2 minus I multiplied by 2 plus I, because the factors of negative 1 multiply to give us positive 1. And then we know that this is going to be a squared plus b squared, where a is 2 and b is 1, and that gives us 5. So we get a multiplied by negative 3 multiplied by 5 equals 30. And we solve and we get a is equal to negative 2. So the unique polynomial with real coefficients that meets these conditions is negative 2 multiplied by these factors. And I'm going to leave it in factored form. Because it didn't ask for standard form, I'm going to leave it in as a linear factorization.